First speaker this morning is Ben Antieau from UIC, and he'll give the first of his 3 lectures on derived algebraic geometry. The title is The Cotangent Complex and the Derived the Rham cohomology.
That's right. So thank you. Thank you for the invitation to be here. It's a pleasure to be back at MSRI. And so I've been asked to give these sort of DAG lectures to also the birational algebraic geometry side. And so I'm going to try to do that. The aim is also to have it accessible to many of the grad students and so forth. So, well, we'll see if we can get some DAG in the bag here. So the plan of these lectures is today I'm going to talk about what will become the basic affine objects in derived algebraic geometry. So in algebraic geometry, the sort of basic affine algebraic objects are, commutative rings. And so today is going to be about the replacement for those commutative rings in DAG. Tomorrow, we're going to talk about the sort of world of derived stacks and geometric derived stacks. And then on Monday, after the weekend, I'm going to mainly give some examples and try to give a flavor of the zoo of different objects that exist once you allow passage to this larger world of rings. OK, so today's about the cotangent complex and derived Rham cohomology. That will really be towards the end of the lecture, because first I'm going to be working towards simplicial commutative rings, which is going to be what we use as our base objects. So, OK, so let me just give a little bit of motivation. And this is 1.1. And so this is going to be a sort of evolutionary diagram. And by diagram, I sort of mean the thing that you see on T-shirts where, the evolution of mammals, or, where dolphins, have evolved from birds or something like that. And so we're going to start with what's basically classical algebraic geometry. And I'll just write in each case a representative member of the genus and or species. And so Pn here I mean algebraic schemes, or algebraic spaces even sort of fall under this first heading. And that's pretty good, and that was studied for a long, there's a lot to say about that. But it's certainly not the end of the story in classical algebraic geometry either. So maybe the next thing that we're going to see in our diagram is something like the Picard stack of, let's just say, a smooth and proper K scheme. So here I really mean the stack. So there's still automorphisms that are given by units on X, global units on X. And so this is say, an Artin stack. And these also go back quite a ways, or Deligne-Mumford stacks would be a subclass of these. And to make the next move in the sort of evolution of these objects, we need to realize a couple things. So these are all certain kinds of sheaves of sets. Okay, so I'm going to really emphasize the functor of points perspective on this. So these are all étale sheaves of sets here. And these are étale sheaves of groupoids in some appropriate sense. And to make the next move, what we want to really do is we want to view this category of sets as equivalent to the category of discrete spaces, discrete topological spaces. So I'm going to write that script S less than or equal to 0. So the less than or equal to 0 just means that there's no higher homotopy groups. So each sort of component is just contractible. Groupoids is equivalent to, say, as a sort of 2-category to spaces less than or equal to 1. So if you give me a space, I can spit out some fundamental groupoid. The objects of this category are points, and then the morphisms are homotopy classes of loops and so forth. And so there's an equivalence of categories here. And now, you might wonder, can we continue on to the right? And so that's the content of higher stacks. And so let me just write down one sort of particular example. I'll write this as KGMN. So this is a higher stack. And what it is it's a sheaf with objects in truncated spaces, n-truncated spaces. So what do I mean by an n-truncated space? So it's a topological space. And at each point, if you choose a base point, there are no homotopy groups above degree n. And these are all kind of geometric objects as well. So these are not just random atol sheaves of sets, groupoids, or n-truncated spaces. They're built out of affine schemes starting in with a few acceptable moves. Okay. And this KGMN is obviously the most exotic thing that I've written on the board so far. What you should think of this is this geometrically has a single point. It's a stack with a single point. But the isotopy is KGMN minus 1. So isotopy is KGMN minus 1. And so inductively, we see higher and higher kind of geometric objects that encode things that look geometric, but live in higher homotopy. Okay. So this, by the way, this is the mapping stack from X to KGM1. Okay. So, and let me just say, just to emphasize before I'm going to continue this evolutionary diagram in a moment, but KGMN, let's just look at KGM2 and KGM1 for a moment. So oftentimes one writes this schematically as being a point mod GM with the trivial action. So this is like some kind of stack notation. Here, what we can view as this, and then this. So also this often goes by the name of BGM. This is the absolute Picard stack. So mapping into this gives you the Picard groupoid of a scheme. And now KGM2 we can write in kind of the same way. This is a point mod BGM or mod KGM1. Okay, and this is a smooth Artin stack. So this is some kind of higher geometric stack that still has some smoothness properties in it, and we'll say a lot more about that in the next lecture. Let me just tell you what it means to give a map from a scheme into one of these particular higher stacks. Okay, so this world of atol sheaves with values in here is enriched in topological spaces. So if I have X as a scheme, and then there's a map from X to KGMN, a mapping space, and this is a topological space. Okay, so what are the homotopy groups of this topological space? So the homotopy groups are given as follows. So pi I of this mapping space is, well, it's degree n minus I atol cohomology of X with coefficients in GM if 0 is less than I less than or equal to n, and it's 0 otherwise. So this is a sort of higher geometric stack that says something about higher cohomology groups. Okay, so that's the sort of object that this is. Now, what we've done now is, and then Sn, obviously, this fits inside of all spaces. So we've just allowed ourselves to look at atol sheaves with values in not just sets, not just groupoids, but some kind of higher topological spaces. We've seen that certain examples of those have some sort of geometric meaning. They control atol cohomology classes, and they're also built out of geometric objects by taking sort of iterated quotients by smooth actions. So here, I take the quotient of a point by this smooth affine algebraic group. Now I take a quotient of a point by this smooth Artin stack, the group object in Artin stacks, and I can keep on going. And that's the fundamental process that produces the geometric higher stacks. So now what we can do is, I want to use this to set up why we might derive things. So what the basic objects in algebraic geometry are these schemes, which are certain topological spaces equipped with a sheaf of commutative rings. But now we're allowing our sheaves to be sheaves of groupoids or n-truncated spaces and so forth. So the basic idea is, well, now that we've allowed these higher stacks into our hearts, which didn't really take long, we can imagine geometric objects where the structure sheaf, OX, is actually itself some kind of sheaf of topological spaces. And that's the fundamental idea of derived algebraic geometry. So I'm sorry, I sort of mismanaged the board here, so I'm going to have to cover this up. So let me give you the next two layers in the evolution here. So the next is the derived schemes. So spec of K, I'm just going to do a very simple version. I take the derived tensor product of K with itself over Kx, where x goes to 0 in both cases. This can be modeled by what's called a simplicial commutative ring. And this is a basic version of an affine derived scheme. Okay, so and we'll see today how to make sense of this object. So this is something you know. This is a complex with homology in degrees 0 and 1. Degree 1 is Tor 1 of K against itself over Kx, right? Okay. Now, once we've gone to affine derived, once we've then start to talk about derived schemes, we can just repeat the same process and start to take stacks. In other words, start with derived schemes and then take quotients by groups and smooth groups, and then just iterate that process. And then in the end, we get, and this is going to be the subject of the next lecture, we get sort of the large world of derived stacks. And so I wrote down a representative object. This is the moduli of objects in C. Let's just say it's a DG category. This is going to be a prototypical derived stack, and we'll study it a little bit next time. Okay, so this is a little bit of the evolution. It doesn't necessarily mean that the end point is better than the other points. I'm certainly not saying that, but that's something about how this has evolved. And so now let me start and try to make sense of all of these objects. So please feel free to ask questions along the way. I'm about to start section 2 on simplicial commutative rings, and I view this as being probably the most difficult section in all 3 talks. Unfortunately, it comes right at the beginning, but what this is we need to agree collectively on what our affine objects are going to be modeled on, and that's going to be these simplicial commutative rings. And I also don't want to lie, so I'm going to give a little bit of details about these, but probably not too much. Okay? So here's the basic idea, and it's motivated exactly by this kind of example, so of this sort of derived intersection. So let's look at the derived category of the integers. And let's look at the connective objects. So these are chain complexes. Let's say C star, where hi of C star is 0 for I less than 0. So I'm working homologically here. Now, we know that there's a derived tensor product on this category that makes it into a symmetric monoidal category. And so the basic idea is we're going to look at, we want to basically look at commutative algebras in this symmetric monoidal category. So this is a totally familiar move. You know, people understood probably in the 60s that you could do algebraic geometry ambient in some symmetric monoidal abelian category. And I don't know how much people have actually done that, but it's been understood that the theory could be developed. So this is just a little bit different. Instead of working in a symmetric monoidal abelian category, we're going to be looking in sort of connective chain complexes with this tensor product. And we can look at various kinds of commutative algebras in here. And simplicial commutative rings are going to be one way of studying commutative algebra objects here. Right, so connective is hi is 0 for I less than 0. So that would be my, it's going to be hard for me to hide some of the sort of homotopy theoretical background. So this would be the same as saying that the positive cohomology vanishes if you're more used to thinking about that. Okay, so so there are a few different ways of making sense of derived algebraic geometry, and so there are sort of potentially three choices we might make. I just want to say this. I'm only going to make one of them, but we can look at E-infinity ring spectra, which makes sense even in here. We can look at simplicial commutative rings. And if we work over the rational numbers, we can look at commutative DGAs. We can look at Q, C DGAs. So I'm going to choose and work in this series with simplicial commutative rings. No, they're not. They're definitely not equivalent, and they lead to slightly different theories. Over Q, certainly these two are equivalent, and I guess this is also equivalent. But over the integers, these are different theories. And over Z, there's not really a good way of doing commutative DGAs in a homotopy theoretic way. So this is a good and concrete version to take. Okay, so let me actually tell you now what a simplicial commutative ring, and that's gonna involve this simplex category. So I'm going to give you first a definition, and then I'm going to tell you kind of a universal property that the category has, which maybe makes it a little bit clearer what's going on. So this simplex category, so this is the category of finite, of non-empty finite ordered sets. Together with order-preserving maps between them. And so the way to sort of view these is as follows. I have this ordered set. I have this ordered set. I had this ordered set. And there are various maps between them. So clearly, I can include this two ways, but I can also collapse this. I can include these three ways. I can collapse these. The ones going up are face or coface maps, and the ones going down are degeneracy maps. This is kind of what this category looks like, and everything, all of the morphisms are compositions of these morphisms that satisfy a bunch of axioms that you can figure out just bearing in mind what these objects are. Okay? So that's what the simplex category looks like. And now if definition, if C is a category, SC, which is functors from delta op to C, this is the category of simplicial objects in C, just by definition. Okay, so let me give you a couple examples here. Yeah, so the question is there a specific reason why we take sort of pre-sheaves on delta instead of the other thing, functors from delta op out instead of functors from delta out? Yeah, let me maybe that'll become clear in just a second from one of the examples. So it's a good question. So let me give examples of three simplicial categories here. So the first one, and this is really where this comes from, so it turns out that simplicial sets is equivalent to the category of topological spaces. And I need to make something very clear here. I'm not saying that these are equivalent categories. So these are equivalent as homotopy theories. So there's going to be some homotopy theory going on under the hood here. So what I really mean is here, and there's a notion of weak equivalence. Here, there's also a notion of weak equivalence. That's sort of familiar if you have a map of spaces, then for each, you want to have isomorphisms on homotopy groups, and then something for pi 0 too. That should be an isomorphism on pi 0, and then for each choice of base point in X, you get this. So that's weak equivalence here. The notion of weak equivalence here is just a little bit harder to identify. But these categories, so the homotopy theory of topological spaces up to weak equivalence turns out to be the same as the homotopy theory of simplicial sets up to weak equivalence. Okay, and so this is a fact that is probably many of you are familiar with. But let me just tell you where this goes. So in here, there's an n simplex, which is just hom from into n, so in delta. So this object, since I'm homming into n, this gives me a simplicial set, right? It's a functor from delta to sets. And on this side, I also have the topological n simplex, which is just the, in coordinates, it's points in Rn plus 1 such that the points are non-negative and the sum of the points is equal to 1. And if you sort of make a functor that sends delta n to delta n top, well, just by Yoneda, kind of the property of such a pre-sheaf category is that it's generated by these representable objects, right? So simplicial sets, its functor is, we could write it as pre-sheaves on delta or functors from delta op to sets. So everything in here is generated by colimits by these delta n's. And so by making this assignment, I can extend by colimits and get a functor from simplicial sets to topological spaces. So the notion of weak equivalence we use here is just pull back the notion of weak equivalence along this functor. Okay? And then it turns out that that is a weak equivalence. That's an equivalence of sort of homotopy theories. Now let me just really quickly describe the functor back, which is called the singular complex construction. So this singular complex construction, well, I look at delta top. So by construction, this is a cosimplicial object in topological spaces. And what I'm going to do, just as a convention, is if I write top in this, sort of in this font, I mean really the one category. And if I write top in the script font, I'm going to mean the sort of homotopy theory I get from that, or infinity category, which we'll learn a bit from Simpson's talks. So this gives me a cosimplicial object. Well, you can guess what a cosimplicial object is. You know, this is just functors from delta to C. So the point, and this is really the answer to your question, is that there's this there's this natural cosimplicial object in topological spaces. And so when I take Hans out of it, into some given topological space, so this is just continuous maps in each degree, I've then opt it, and this is a simplicial object. And that's the right adjoint to that map. This is actually familiar if you've seen singular homology before. If you've seen singular homology, then we can do the following thing. This is a simplicial set, so I can make it into a simplicial abelian group just by taking the free abelian group in each degree. In other words, that's composing. I have a functor from delta op to sets, and then I have a free abelian group functor from sets to abelian groups. So that's what this is. And now from such a thing, I can cook up a chain complex. Okay, so let me explain that in the next board, and but let's just say now I can cook up a chain complex from here, and the homology of this chain complex is isomorphic to the singular homology of X with coefficients in Z, as you would learn about it in algebraic topology 1. Okay? So in some sense, you've already seen this kind of construction, probably. So so that's our first example, simplicial sets in topological spaces. And so so B is I can take simplicial abelian groups, and we've just seen an example of one of those. This is a simplicial abelian group. And the derived category of K, the connective objects, of Z, I guess. The connective objects. And once again, these are equivalent as homotopy theories. So there's a notion of weak equivalence here, just given by quasi-isomorphism, and there's a notion of weak equivalence here, which is just map, forget to simplicial sets and then map to topological spaces and ask if they're weakly equivalent. Okay, and so these two things turn out to be equivalent. And a specific way of doing this is the Dold-Kahn correspondence, so which takes a simplicial abelian group, and let me call such a thing just m dot. And let's look at the low degree information I have. I have these two face maps coming from the simplex category. I have three face maps and so forth. And I'm going to construct a new, I'm going to construct a chain complex where in degree 0 I just have m0, but the differential is given by summing up by the alternating sum of the face maps. Okay, so these are the unnormalized chains that I'm saying, and the homology of this chain complex turns out to be the same as the homotopy groups of this simplicial abelian group when I just view them as a topological space. And C, simplicial commutative algebras over some base commutative ring K. So this is going to be the thing that we care about. So this is functors from delta op into commutative K algebras. And this is going to be the home for derived algebraic geometry for us. So so this kind of object was studied by Quillen and really was one of the reasons model categories were created to begin with. I'm not going to say too much about that, but again, there's a notion of weak equivalence. The notion of weak equivalence is just, again, forget all, a simplicial commutative algebra has an underlying simplicial set. The weak equivalences are just the maps that are weak equivalences as simplicial sets or as topological spaces. Okay, but there's a little bit more than that. There's this model category structure, which I don't have time to get into, but what that means is that the model category structure gives you a notion of weak equivalence and also a right way of doing things. This is just like in the derived category of a ring. There's a right way of making computations, and that right way is take resolutions everywhere. And so the point of simplicial commutative rings is it gives you a way to take resolutions of commutative rings and to make constructions with resolutions of those commutative rings. And so this is sometimes called like a non-abelian derived category construction. And we'll see a couple examples in just a moment. How are we doing here? Probably very poorly. Oh, right. So let me say just a general fact. If I have a simplicial commutative ring in here, then there's a graded, then pi star of R, or what's the same is the homology of the associated chain complex. This is equipped with a graded commutative ring structure. Okay, which means that if I have two elements, then they commute up to this sign rule, given where x and y are the degree and the homotopy. It's even a little bit better, odd degree classes squared to 0. Okay, so that's the kind of thing that's underlying. You can just think of this. We get this associated simplicial we get this associated graded ring, which is kind of helpful. And yeah. So now let me. Let me give a slightly different perspective on simplicial commutative rings, which it kind of is about this resolution business. Right. So let's just look at, there's an adjunction from, yes?
You are in acoustic theorem. The rationals is the map that takes the simplicial object to the complex fully faithful.
So if you do, so there's a slightly different there's a slightly different normalization called the normalized chains, where they're just equivalent categories. That works over the integers. So in fact, ignoring this homotopy theory stuff, simplicial abelian groups is actually just equivalent as a category to chain complexes of abelian groups concentrated in degrees at least 0. So they're just the same category. But that's a slightly different functor here. It's not particularly, it's not too important, the difference. Does that answer your question? It doesn't look like it.
My real question was, can you recover the weak equivalences as quasi-isomorphic?
Oh, sure, you can as well, yes. Yeah, sorry. Yeah, exactly, yeah. So under that equivalence, they're really sort of also equivalent as sort of homotopy theories, yeah. Okay, so I have this adjunction from sets to commutative K-algebras. And this, this is just forget the fact that I have any structure on the set. And this sends a set S to K adjoin S, the polynomial ring on those generators. And anytime I have an adjunction like this, if I give myself an object R inside commutative algebras, I can cook up a canonical simplicial resolution, which I'll call S dot, and a map to R. And this S dot looks as follows. In degree 0, it's K on the set of elements in R. It's the free commutative algebra, just we forget that this has any structure. And you can use the co-unit map and so forth, the co-unit and unit maps of this adjunction to build a canonical simplicial object. And this is a homotopy equivalence. And so what we've done is we've taken any commutative K-algebra, and we've found a canonical simplicial commutative K-algebra, which degree by degree is actually given by polynomial rings, possibly typically in infinitely many variables. And it has the same homology. So what you should think about this is the analog of a projective resolution. Okay, so think projective resolution in homological algebra. Okay. So what that lets me do is now, let's suppose I have a functor from calg K poly. So this is finitely generated polynomial rings. And I take a map to any other reasonable category or possibly infinity category, whatever that means. So the point is, so this includes into what I'll call ind calg K poly. And then this includes in simplicial calg K. So let's suppose C, so here I just mean, by ind, I mean formally adjoin filtered colimits. So formally adjoin filtered colimits. So if I start with finally generated polynomial rings, any polynomial ring on infinitely many generators is in here. Now, if C has filtered colimits, there's a unique functor here that just extends this, right? By just, applying it to each, applying it to some colimit diagram that gives you an object here. So let's call this F, this functor. I'm just going to call this also F because we've just extended by colimits. It's not terribly hard. And now, there's a derived, if C has certain colimits, there's a derived functor that I'm going to call LF. And that is, that's constant, the constant diagrams. Thank you. So if I have a commutative ring, I can just view it as a constant simplicial commutative ring. Yeah. And I'm not saying it is, because there's no simplicial here or here. Yeah, absolutely. So if I start with a functor that's just defined on finitely generated polynomial rings on affine spaces, I'm going to cook up, I'm saying there's a way to cook up a new derived functor that, that's defined on all of these. And so here's what the recipe is. So now let's take R inside calg K, and I'm going to look at its simplicial, this canonical resolution. Now, each of these is an infinite dimensional polynomial ring. So I can apply F level-wise to S dot. And that gives me a new this gives me now, this is a simplicial object in C. And now I can take the colimit over delta and just force this. Take the colimit over delta, which is also written as the geometric realization of that S dot. And this, by definition, is LF of R. So I just gave you a recipe for starting with a functor just on polynomial rings and cooking up a new functor on all simplicial commutative rings, but one that in particular, if I take just an ordinary ring that's not like smooth or not polynomial, then I can get this LF on it. And so now, just in the interest of time, I mean, it turns out that this category has a universal property. In other words, functors out of this category are just equivalent to functors out of this that satisfy some certain properties. No, right. I mean, let me write ho colim if you prefer. What? Why do I assume polynomial? I guess that's just the construction that I'm making. What? Yeah, I mean, this is what I want to do. Maybe we can discuss alternatives afterwards. So it's a homotopy colimit. So there's I mean, I'm being rather vague because I don't want to. I mean, secretly everything in sight is an infinity category, but I thought that might be unpalatable at the moment because we haven't heard Carlos Simpson's talks yet, after which it'll be fine. And so really what this means is just like in a derived category, there's kind of a right way to take a colimit by taking some resolutions and things like that. I'm assuming C is that kind of object where there's a right way to do things. Well, no, but now I guess I'm saying this is a Kahn extension, in other words. So this is now defined for any C, and in the right setup, this will be homotopy invariant. So if you have two equivalent objects here, it'll spit out equivalent objects here, and so forth. So. Right. So if you have a general simplicial commutative algebra, then you can do this canonical resolution degree-wise and replace it with an equivalent simplicial commutative algebra, which is polynomial in each degree. And then you could do this resolution if you want. Yeah. So there's some, maybe I won't get into it too much more, but the upshot is to give a functor out of just finely generated polynomial rings to C is the same up to some sort of, depending on what colimit preservation you impose, to giving a functor out of simplicial commutative algebras. Okay, so that's probably, I had better move on. So let me give an explicit example of this, because that's the point here. So the cotangent complex. And so this is, there are three different ways to view this cotangent complex, and they're all equivalent. And the first one is just to use this derived functor approach. So suppose I have K mapping to R. This is just a commutative ring. This is a commutative ring. And now I'm going to look at my canonical resolution. And so this is just going to be the derived functor of taking omega 1. So, oh no, that's B, actually. Sorry. Hold hold that thought. So what I can do is I can take omega 1 s dot over k. So I can just take Kähler differentials degree-wise. And then I can base change along this map. This is now a simplicial R module. Okay, so this is in simplicial mod R. And I can then use Dold-Kahn to view this as an object, a connective object in the derived category of R. And what this object is by definition, the cotangent complex of R over K. Okay, so that's just a definition. Probably by itself, it's like, well, yeah, I could have done that with any functor. What, doesn't. It's maybe not so interesting, and it also leaves open a bunch of questions, like, what if I had taken a different resolution, not the canonical resolution, but some other one? Would I get the same cotangent complex? It turns out the answer is yes, but this particular definition doesn't make that completely transparent. So let's see. So B, I can do the following. I can take finally generated polynomial rings, and I can just map them to the derived category of K. This is just take omega 1 of your polynomial ring over K. So what did I write here? More than or equal to 0. So the connective objects. And then this includes into simplicial guys, and I can just take the derived functor of this. And that will also spit out the cotangent complex. Okay, in exactly the same way. So that's another way of thinking about this. So this one, it's not quite clear, how it depends on the resolution. In this one, it's not quite clear, like we should have landed in R modules, not in K modules, right? So it's not completely clear how the R module structure on this works. So the better way to view this is as a universal property. And the thing is, this universal property only really makes sense when we're working with simplicial commutative rings. So let me give you the universal property. So let's see. So let's say I have K to R to S. And now this is this is a commutative ring. These can both be simplicial commutative if you want, but maybe we're mostly interested for the moment when R is an ordinary commutative ring. Now, what we're going to do is find a universal property for the cotangent complex. So an M and S module. Okay, so once again, I'm using the fact that, so these are both M and S module in the derived category of S more than or equal to 0. So these are connective. Once again, I'm going to use the fact that there's a natural sort of enrichment in topological spaces. So when I write map, I mean that this is a topological space. Okay, so it has homotopy groups, pi 0, pi 1, and so forth. And the universal property that this has is that this is naturally equivalent to maps in a different category. So let me write. I'm going to write it. Oops, sorry. So so this is the category of simplicial commutative K algebras equipped with a fixed map to S. Okay? Simplicial commutative K algebras, a fixed map to S. So this is like a comma category. And in here, I have the following objects. I have R, and I have R plus M, S plus M. And these are both objects in this category. R because it has this fixed map to S, and S plus M because I can just I can map down to S. So this is the square zero extension. And the point of simplicial commutative rings, one of them is that this square zero extension still makes sense even if M is a chain complex. It's still possible to make that into a simplicial commutative ring, okay? And when you do that, this is exactly the universal property that the cotangent complex has. Now, this might look familiar to you, because if you did all the exercises in Hartshorne, which I think I can safely assume, you know, this looks awfully like the definition of Kähler differentials. Okay? And so here's an exercise for you. Prove that pi 0 of the cotangent complex is isomorphic to the Kähler differentials. Okay? Just using the universal property that I just showed you. Okay? Because that's exactly lifting through the square zero extension, right? This is this sort of thing where we have R to S and S plus M. And giving this map is like giving a derivation from R into M. And so one just abstractly defines this as being the space of derivations of R in M. Whatever that means, it doesn't quite have as explicit a content in terms of like, you know, of formulas with elements in them. But that's given by this mapping space in this comma category. Here are two more exercises that you can do just using this universal property. And I mean, you can really actually do these. So you can prove that in this setup, so I can base change the cotangent complex of R over K to S, and then go to the cotangent complex of S, and then go to the cotangent complex of S over R. And this is an exact triangle or a cofiber sequence. You can use this, so I'm saying use this universal property, and you can prove this. So this is like the transitivity. And the other thing that you can prove is that if you have a diagram like this, T and R tensor K L T, then if you take T tensor over K with the cotangent complex of R over K, you get the cotangent complex of R tensor L K T over, let's see, how did I do this? R over K over T. So do these exercises. And you can use, so these are basic facts, if you like, and you can really use just this mapping space property. And you have to think about a little bit what it means to compute maps in a comma category. Okay, and but that's a little exercise itself. Okay, I think I'm going to 10:35. I think I start about 5 minutes. Okay, oh, and let me give one more exercise. I guess I'm just gonna give exercises instead of explanations for time reasons. So let's let R be a perfect FP algebra. That means that the Frobenius map from R to R, which takes x to the p, is an isomorphism. So prove that the cotangent complex of R over FP is 0. Okay, that's another exercise to do. Now, yes, let's see. Okay, yeah, let me skip that for now. Well, okay, let me think. So, okay, so we'll come back to that. So let me now talk about derived Rham cohomology, just so I kind of satisfy the title. And we'll have more to say about the cotangent complex in later lectures. So here's a specific functor I can make from finally generated polynomial rings to chain complexes over K. So I can just take a polynomial ring, let's just call it R, and I can map it to the de Rham complex, the algebraic de Rham complex, which is R, omega 1R, omega 2R, and so forth, R over K. And OK, so this is nice. Since this is finally generated, this actually stops at some point. And now I can just formally extend this to get L, let's see, what should I call this de Rham complex? I'm going to call this de Rham complex R over K. So I can get L de Rham blank over K, a new functor, just by deriving this de Rham complex. So this seems maybe a little bit abstract, like what, you know. But the point, the underlying point is that we know that de Rham cohomology behaves decently well for smooth things. And we want to extend that fact and the things we know about it to non-smooth things. And so this is going to give us one way of doing so. But there's a little warning to make here. So suppose K is a Q algebra. So we're in characteristic 0. Then what is, and R is a polynomial ring. What is the de Rham complex of R over K? Like up to what is the cohomology or homology of this complex? Well, the Poincare lemma tells us that this is actually just given by K. Okay, we're doing the de Rham cohomology of affine space. So nothing interesting is happening here. Okay, so we get just K, and that means that when we do the L de Rham blank of like anything S over K, any simplicial commutative ring, I get K as well. Okay, so I think we can agree that's sort of disappointing, kind of a problem. And so the solution to this, I actually have, I mean, is this due to Barkov? I guess this is probably due to Barkov, but. So the solution to do this is, well, we have more information than just the complex. We actually have the stupid filtration on the complex, namely the Hodge filtration. Okay, so I actually have the Hodge filtration on the de Rham cohomology of a finitely generated polynomial ring. And what are the graded pieces of this? So the ith graded piece is omega I R over K sitting in, well, homological degree minus I, cohomological degree I. So I guess kind of working homologically everywhere. And taking these gradings is compatible with colimits. So what I can do instead is I can do the same con extension, but where I remember this filtration, this Hodge filtration. So I can get a canonical Hodge filtration on the derived de Rham cohomology. Okay, so let's call that F star H L de Rham blank over K. And what are the graded pieces of this? Well, the graded pieces, formally, just because of what happens when you extend these functors by colimits are you take the derived exterior power of the cotangent complex of R over K, and you shift it into degree minus I. So this is the ith exterior power of omega 1 R over K. And because kind of the order doesn't matter when you take the graded pieces or not, what you see is that when you do this Kahn extension on the graded pieces, you're deriving this functor. And that gives you this derived exterior power of the cotangent complex. So this gives you a new filtration. This gives you a filtration on the derived de Rham cohomology. And let's just write L de Rham hat for the completion with respect to this filtration. Okay, so the completion, so this filtration isn't complete. So what does this mean? This means I take the limit, just like all completions, it's the limit of the derived de Rham cohomology of blank over K modded out by F by the ith stage of the filtration. So just like taking the p-at-x as the limit of z mod p to the n's, it's the same thing. So you take this limit, so you make it complete. And now let me just state a theorem in the last minute. The argument on the right? Oh, you mean like I here? Is that what you're? You take the derived de Rham, you take the sort of total derived de Rham cohomology and you mod out by the ith piece of the filtration. I just wasn't going to write this. Does that answer the question? Sorry. Okay. So let me just state my theorem because I know, not my theorem.
It's a little confusing because there's a ring R which sometimes appears and sometimes doesn't appear in the notation.
R is for Rham. Oh, yeah, sorry. Okay, yeah, fine. No. Let's, is that, okay, now there are no yeah, okay, thanks. So here's the theorem, which is basically due to, not in chronological order, so maybe Bach, Grothendieck, and Hartshorn. So let's suppose that I have x over the complex numbers, which is finite type. And I take this sort of L de Rham cohomology, and I take the global sections over x of this OX over K, and I've completed it with respect to this filtration, then this actually turns out to be the same as the singular cohomology of the complex points of C with C coefficients, which is, I think, a pretty amazing fact. So this is a generalization of Grothendieck's theorem in the smooth case. And then Hartshorn made a notion of algebraic de Rham cohomology, which is a different construction than this, but Bargov showed that those constructions agreed. And one of maybe the sort of features of this construction is that it doesn't depend on the choice of putting x in an ambient smooth scheme. So I'll stop there. So I don't completely understand the question, but maybe, so the question is this my model for the derived category of simplicial commutative K-algebras? Oh, yeah, right, exactly. So the analog, you're right, that's right. So simplicial commutative K-algebras is to ordinary commutative K-algebras as the derived category of K is to K modules, ordinary K modules. But maybe we want to say connective, but whatever. I mean, so yes, that is the exact analogy. And let me just say that these are going to be our affine, these are going to be the coordinate rings of our affine objects in derived algebraic geometry starting tomorrow.